Hello, everyone, and welcome to today's presentation on computational storage, driving success and driving standards. My name is Jason Molgard, and I'm with ARM, and along with my co-presenters, Bill Martin from Samsung, Oscar Pinto, also from Samsung, and Scott Shadley from NGD Systems, we'd like to give you an overview of what's going on within SNIA as it relates to computational storage and what we're up to and where are we heading next. So a little bit more about our speakers today. So Bill Martin from Samsung, as I mentioned, is the editor and of the SNIA computational storage architecture and programming model. I'm Jason Molgard, as I mentioned. I'm from ARM. I'm one of the co-chairs of the computational storage technical working group. I'm also a member of the CMSI computational storage uh, special interest group where we work on promoting the computational storage standard. Oscar Pinto, also from Samsung Semiconductor, is an editor and works on the computational storage API. And our fourth presenter is Scott Shadley from NGD Systems. He is my co-chair on the computational storage technical working group and will be presenting as well. So as with all presentations, here's a quick legal notice from SNIA. This material is copyrighted by SNIA, and lots of legalese here. But I think the key line item is at the bottom. There's no warranties expressed or implied, and you must use it at your own risk. Feel free to read through the rest of it at your convenience. So SNIA at a glance. So we have 185 organizations that are member of SNIA that work together in a collaborative fashion, 2,000 contributing members, and overall 50,000 IT end users and storage pros worldwide are involved in SNIA or participate in SNIA events to one degree or another. So next, we'll jump into the computational storage section, a quick history and some status as well. All right, so it all started out a few years ago. We wanted to set some common language, common goals for computational storage, and make sure that we're all on the same page. This is, this is kind of one of the challenges with any new technology, is we need to be able to say the same thing and mean the same thing and all speak the same language. So computational storage had many names, even as far back as 2010. There was, scale in situ processing, compute in data processing, and we needed to obviously standardize not only on the name but also on everything that was going on as it relates to computational storage, so that we could all be on the same page. So part of the effort that came out of the computational storage technical working group is a taxonomy in order to help level set all of us and bring us all onto the same page. And that's part of the reason why the technical working group was formed, so that we could work together collaboratively and ensure that we came up with terminology that we could all use and leverage and accept as we moved forward and help develop this and bring this technology to the market. So the
Hi, this is
ongoing,
Scott. Can you hear me now?
yeah, hi Scott.
My sincere apologies to all the attendees. I had some audio difficulties. Jason's done a great job covering my section of the presentation. I'll jump in and give him a breather till he gets back to his part. It's a wonderful thing that we've had this opportunity to get going. If you pay attention to the picture on the last slide or go back and look at that, you'll see that we started with a very small group of people. As of today, the ongoing work that we've done to work on this concept of computational storage to define the standards, the working group has grown considerably. The member count of the actual work group that we're doing within SNIA is up to over 261 individual members representing 51 unique companies. And we find this very unique in the fact that a lot of people look at industry organizations as a bunch of creators of content trying to push that content forward. What you'll see from this particular participation list is we not only have that going on, which is a traditional way to get technology moving forward, but there's a lot of consumers of the technology that are also now participating in this work group. So we've had the opportunity over the last few years as this group has evolved to start from where we think it could go to how people could consume it and evolve it even more from there. And as we did that, we also created what's known as a special interest group within SNIA, and that's what's represented by the four members here today, where we are the marketing arm of the technical work. So SNIA has done a really good job of separating, let the techie people do the tech work, and let the marketing people do the evangelization of that effort and leverage the technical content and stuff. So this webinar represents some of the work that that special interest group is doing. Now, as an organization, we also know that SNIA can't do this in a a biosphere of sorts, if you will. We need to collaborate with the rest of the world and the organizations out there that are also doing other work. So we have partnered and have a collaboration platform with our friends at the NVMe Express, who are driving the leading edge SSD communication protocol over PCIe. And they have actually got a task group within their organization that's doing things around computational programs. So you have SNIA, who's driving an architectural view, which we'll get into as part of this presentation, and NVMe driving a specific implementation. And there's lots of additional work that's continuing to be done in that space. So Jason and I also did a great overview at the Storage Developer Conference for purposes of giving more of a detailed background on what's going on with this particular process. And that's still available to register for and view that content as well. So there's a lot to be said about what's going on within the SNIA as an organization, but there's also a lot to see what's happening when you get the technology moving out into the industry and the visibility of that. So as Jason so kindly pointed out, there were a lot of different names for this overarching architecture. What we've done now is with this term computational storage, it's allowed us to go out, communicate, evangelize, and then have people request interest in this type of technology. So you can see, for example, Computer Weekly just this year completed a 13-part series. They went out and talked to member companies, they went out and talked to consumers, and you can see a whole bunch of the headlines as they wrap around this the particular picture in the middle here on their analyst series. So they did an analyst series and a developer series and talked to quite a few different people. Another aspect of driving standards work, new technologies forward is engaging the analyst community and forward-looking architectures like that. So our friends at Gartner have this process they call a cool vendor. Two of the member companies have received that acknowledgement from Gartner, as well as this concept of the hype cycle. So we all know, there's various different industry groups that talk about different products and different solutions. The hype cycle, for example, represents some of that unique architecture that's available to drive technology forward in a different view of that marketplace. You can see that computational storage, in its uniqueness, has been able to enter into two separate spaces around that. And that would be the compute infrastructure, the computational side, and then the storage and data protection roadmaps as well. And it's very well on its way to becoming what they classify as a standard issue product and technology. We also have this concept of what we're classifying as sponsored efforts. So again, outside bodies presenting and supporting this technology work. The logo that's labeled EMC3 is from our friends at Los Alamos National Labs. It's a consortium around computing and efforts that need to take place for that to be able to be driven things forward. And it's high performance computing and other aspects of government entities. The next one over is a presentation that was done by VMware at VMworld 2021, and they did an update in their, or 2020, and they did an update in their 21 series. It's an Office of the CTO effort. And then the bottom image there represents Dell Technologies highlighting their potential future moving forward as far as what can be done with this architecture and technology for purposes of driving things forward. So lots of unique opportunities and direction that are taking place because we came together as a group of individuals and said, let's make things look and feel the same. So again, I'll apologize for some of the technical difficulties I drove at the beginning of the session, and we'll continue forward and hand that back over to Jason.
Yeah, thank you, Scott. So now we'll kind of take a look at some of the work that's being done within SNIA on computational storage. But before we delve into some of the details, maybe it'd be useful to start with a potential use case for computational storage. Without necessarily getting into a lot of the details of the use case itself, the picture over on the right-hand side shows how computational storage drives can be connected both to the CPU directly and through a network like a NVMe over Fabrics type network, and even be part of a computational storage array. And all of these words that I've just used, we have definitions for them, and we can get into a little bit more detail here and in the upcoming slide. But essentially, as a potential use case, you can have the drive generate metadata on a set of data that's on the drive, and then send it up to a host for further processing. So again, I won't get into any more detail than that on this potential use case. So what are the use case, or what is the progress, and what is the twig working on? Well, we've got a couple of documents that have been prepared at this point. The first one is an architectural document. It's been released. Version 0.8 is available and out for public review. We've made many updates from the 0.5. So if you haven't already seen this, we encourage you to download a copy, and we would welcome your feedback. Any input that you have that we could consider for enhancements or changes. And then likewise, we also released an API document. The version 0.5 is now available for public review. And again, this can be downloaded. You can review it offline and provide feedback. We would welcome that. Kind of the next area that we're focusing on is related to security, and we're doing that in collaboration with the SNIA security twig, as they have a lot of security expertise and experts over there who can kind of help provide some guidelines for us and guidance. But in today's presentation, we're going to focus only on the architecture and the API, given that there's still a lot of work to be done on security. So early on, I mentioned, and then Scott reiterated the need for a taxonomy on computational storage. So using these three diagrams here, let's try to establish a little bit of that taxonomy uh, up front before I hand it over to my colleague to continue the conversation. So if we take a look over on the left-hand side of this diagram, we have what's shown as a computational storage processor, or CSP. So this is a device that would have computational storage resources or a computational storage engine that's able to perform computations or some type of function on data that's on in a storage system, but it does not actually have any of the persistent storage for that storing that data. That's somewhere else in a traditional SSD perhaps. In the middle diagram, we have a computational storage drive, and it has those same computational storage resources, but it also has the persistent memory for storing data. So you can think of a traditional SSD with additional capabilities. And then over on the right-hand side, we have a computational storage array, or CSA, and essentially this is a storage array that contains one or more computational storage engines. So you could have the engine up in a higher level, as it's depicted in this diagram, or you could even have that plus and/or a computational storage drive as part of the array. So now, with those kind of three terms out of the way, two of which you may remember I addressed in the use case slide a few slides ago, let's delve into a little bit more detail on the computational storage resources. So if we look at all three of these diagrams, they all have kind of a teal colored computational storage resources block and a lot of different acronyms there. So let's take a look at some of those. So the computational storage resources are essentially all of the resources that are available for performing a computational storage function, also known as a CSF. And you'll see CSF in a couple of different places on this diagram. There's a CSF in the resource repository and a CSF within the CSEE. And I'll get into a little bit more detail on what that is in a moment. So thinking about the resource repository, the best way to think of the resource repository is a place where the computational storage functions and the computational storage engine environments, or CSEEs, can be stored. They haven't been activated, but they're available to be activated. You could use them if somebody enabled them. So the big green box, the computational storage engine, that's the engine that's actually going to perform the compute function, or is able to perform the computational storage function, whatever that may be. This could be any number of different things, but maybe one example is a general purpose CPU. You could think of that as a computational storage engine. And within that, we have a computational storage engine environment. And probably the best way to think about a computational storage engine environment is, this is, sets up the operating environment for the computational storage engine. So you could think of an operating system, for example, that has to boot onto that CPU as an example for performing a computational storage function. And a computational storage function is the actual function that we want to perform on the data that's stored on that drive or stored in the array or connected up through the computational storage processor. And now that computational storage engine and the environment and the function, they may need some memory in order to operate. And that's where FDM comes in, which is the function data memory. So this is the memory that's available for this computational storage function to execute, to operate, to have as scratch resources, whatever is needed for its operation. And in particular, there's the allocated function data memory, the AFDM, that's been allocated to a particular computational storage function. And that's the memory that that particular function is using. So all of these terms are defined in the architecture document. There's some of them are also in the SNIA dictionary, and but to get into more details about exactly how these terms are then used and carrying forward with computational storage, I'd like to go ahead and hand it over to my co-presenter, Bill Martin.
Thank you, Jason. So building off of what Jason has talked about, I'm going to talk first about implementing the taxonomy of computational storage. So we have a CSX, and a CSX is a term that we use to define any computational storage device, whether it is the processor, the drive, or the array that Jason just talked about. And so that CSX has properties of it. Within those properties, you will find that there are properties related to a computational storage engine. That computational storage engine, it has an engine type. Jason mentioned one type, which is a general purpose CPU. Another type may be an FPGA. And there's other potential types available. Within that computational storage engine, you also have resources. So if you have a general purpose CPU, you may have multiple cores within that. So those would each show up as a resource. So the engine itself has different resources. Then you have the computational storage engine environment. And of note here, when you get to the info that is in each of these, you'll notice some footnotes. The plus in this box indicates that it exists in the repository that Jason showed. The up arrow indicates that it was hard-coded within the computational storage engine. So you may have an engine that has a hard-coded environment. In particular, if you are working with a computational storage device that is an FPGA-based device, there isn't something like a Linux kernel. The environment is just part of that FPGA. But for a CSEE, an environment that is not built into your computational storage engine, then you have the concept that Jason briefly mentioned of activating. So you have to activate a particular computational storage engine from your resource repository on a particular computational storage engine. So once you've activated the environment on the engine, now you have an environment that you can now perform computational storage functions in. And the computational storage functions have the same characteristics where they may be hard-coded within the environment, or they may just be in the computational storage resource repository. Again, in order to actually utilize any computational storage function, you have to activate it. Now you're activating the function on a particular environment, which in turn was activated on a particular engine. In the simplest case, you have one engine with one environment and one or more functions. In a more complex case, you could envision a computational storage device that actually has a general purpose CPU that you can then run a Linux operating environment on, can then have within that environment, have a packet filter that runs functions, and the functions are actually packet filter functions. But on that same device, you may also have an engine that is an FPGA. And the FPGA may be hard-coded to run a particular function, for example, a function to do encryption and decryption. And so that FPGA would have a hard-coded environment and a hard-coded computational storage function on it. And you could have both of those on a single computational storage device. So with kind of that overview, I want to move into 3 different examples of how computational storage can be used. So the first is a direct computational storage implementation. In this implementation, we are assuming, first off, that data on which computation is to be performed is already placed in the function data memory, or the FDM, prior to sending a request to the computational storage engine. The process for moving that data into the function data memory is not shown in this figure. Result data, if any, is returned to the host through some process that is also not shown in this figure. The figure is basically portraying that you operate on data that is in function data memory and you put the results back there. So what's the process? The data is already in function data memory. The host sends a command to the computational storage controller to invoke a specific computational storage function. The computational storage engine performs the requested computation on data that is in function data memory, places the results back in function data memory. And when it's completed that, it sends a return response to the host to indicate that the computation is done. At that point in time, the host, through other mechanisms, can move the data from function data memory into device storage or back into the host, wherever it is that particular results of the computation are intended to be stored. The next example is computational storage on device data. So this is computational storage that is performed on data that is in device storage. So in this particular example, the host sends a command to invoke the computational storage function. The command specifies the device storage location of the data. So number 2 is actually that the computational storage function, or the computational storage engine, moves the data from device storage into function data memory. Once it's in function data memory, then you do the same thing that step number 2 on the previous slide showed, where the computational storage function performs that function on the data that is in function data memory, and it places the results, if any, into function data memory. Once it's placed the results there, it may, if specified in the request, move those results back to device storage, or it may simply return a response to the host and leave it to the host to move that result data wherever the host wants that to finally reside. So if it's back in the host would do a read command of the data in the function data memory. The third example is indirectly using computational storage on device data. Now, this is a little bit more complex. This particular example is assuming that it is a device-to-host operation. The host sends a storage request to a storage controller where the storage request is associated with a target computational storage function. The storage controller determines what computational storage function is associated with the storage request. Now, there are a few possible, there are many possible means whereby the storage controller can know that a storage request is associated with a computational storage function. One of those is that you have pre-configured to say that a certain range of logical block addresses, whenever you write to them, that you always perform a particular storage function on it, say encryption. Another is that you say, anytime I get any write command, I perform some particular computational storage function on the data. The other is there may be the possibility that you actually have some information in the storage request that indicates that while this is a write operation, it is also associated with some sort of computational storage function. Those specifications have not been developed. We're talking now at an architectural level of what is possible to do with this. So step one was that the host sent a storage request to the storage controller. Step two is the storage controller moves data from storage into the function data memory. Then, as in the previous slide, in this case, the storage controller instructs the computational storage engine to perform the indicated computation on the data in the function data memory. Once that is done, the computational storage engine places the results into the function data memory, and the storage controller at that point returns the completion results, if any, from the function data memory to the host. So this allows for a indirectly using computational storage where you don't actually have to send commands to do it, but you merely operate on the data that's flowing through it. Now, in order to do all of these things, we've worked on developing an API that provides an interface between an application and this overall architectural model. And so I'd like to now hand it over to Oscar Pinto, who will in turn be talking about the computational storage APIs.
Okay. Thank you, Bill. So far, we have gone through where SNIA started on the computational storage journey, the work we have done, and we have touched on the architectural model and the usages of how to use computational storage. What we'll do now is we'll go over the API library, and I'm going to cover what is the API library, how you could use it, and I'll use an example on converting a regular program into a computational storage enabled program using these APIs. So the API library, the way we have gone about it is it should cover all the known types of devices that we have defined today. And I think we touched on this a little earlier, that basically, broadly, there are three types of devices. Basically, the computational storage processor, a computational storage device, and a computational storage array. Now, one API across all these different device types, and that means it's just one common set of APIs for these different devices. And now, this is very different from some of the existing technologies that have been around, wherein you have very specific APIs or very specific interfaces for these. Now, along with that, what we also propose is this interface would connect to different types of devices. And I think Will just touched on it earlier. It could be an FPGA, it could be a CPU, it could be a dedicated hardware like a DPU and so forth. So you could have different types of devices, but they connect to the same API. And these devices could be connected locally, be it PCIe, custom, and so forth, or they could be networked. That is, they're remotely connected through something like NVMe or Fabrics or any other types of network-based computational storage devices. Now, as we know, because these could be different types of devices, they could have different implementations. And what we plan to do with the APIs is hide these different interfaces using the common set of API. That is, the vendor-specific details are excluded or they are hidden from the common set of APIs. By doing so, we're kind of abstracting what the devices can provide, but at the same time, provide all those capabilities. Along with that, we have this goal of making this APIs being OS agnostic. That is, they will work across different OS types once implemented. And as you can see on the right, we have an overview of how a library would sit in your common kernel versus user setup, or local versus remote. So that's why we're referring to as the fabric. So as we dig in deeper about the library, what we're also saying is, yes, this is a common set of APIs. Now, these APIs would manage a CSX across its own device stack. And how do we do that? So we define something that we want to call as plugins. And these plugins are basically an interface between your vendor-specific stack, be it, or maybe a more standardized device driver-based stack. And the plugin will abstract that specific interface into the API, CS API library. What we get by this is that common library across these different types of devices. This also makes it extensible and usable for future types of devices and so forth. Along with that, what we have done is we've set up goals on what this devices, what this API connecting to the devices should be. And from the requirement point of view, we already covered the first one, which is a common interface. Along with that, the APIs will provide you the capability to discover these devices, provide you access to those devices. Now, these devices would have their own memory, because that's the capability that helps you load data close to the compute and so forth. So allocating memory on the device and mapping it, if it is mapped into the host address space, or if it is not mapped, which is it provides a set of APIs that helps you still allocate that memory and use it for computational storage. Along with that, data movement from storage into that memory, so compute could work on it, and copying data into that device memory, be it the input or the results, the output, back to the host. We also talked earlier about downloadable functions. Now, the device could come with some built-in compute functions, and these functions could be something that Bill covered earlier, like it could be encryption, decryption, typical storage services, or it could be something more, let's say, analytics or something of that type. So they could be built in by the vendor, provided by the vendor, or they could be downloadable if they are programmable functions. that written in software. Along with that, these functions could be executable, and that is the whole part about computational storage, where the interface provides you a mechanism to download functions, to execute those functions that are built in and also downloaded. And overall, the APIs have a requirement to make sure that you can configure and manage these devices, at the same time provide the level of security as defined by the specifications. All right, so with that, let's cover an example of an application on the left. So this application loads data from your storage device into the host DRAM. And once the data is loaded, now this data seems to be encrypted. So it loads the encrypted data into the host DRAM. And once it is loaded, it instructs the host CPU to work on that data, that is to decrypt the data. And once that data is decrypted, it goes back to the application. Now, very simple use case. And let's use this example to convert it into a computational storage enabled application with the API library. So with the API library, we used a queued model, which helps you make use of the additional performance features that the device may have, and all new types of devices, including NVMe, provide a queued model wherein the device can do more than your typical one queue depth device. So a queued model, you queue the request. Now here the request would be, you have some input, you have the data that needs to be worked on, that is the compute, and then you have some output, that is the data needs to be copied back to the host. So you queue those three requests in a way that using the APIs to do load the data, then compute on that data, and then provide the output. So once the data is queued, the data is loaded directly into the device's memory, as you can see, which means it doesn't cross the host device boundary. And as you know, you only have so much of bandwidth that is available, be it PCI or network, for the data to travel across. Because as you load more devices on a system, you lose out on that capability of how much data could travel back and forth. So computational storage enables this capability that data is loaded within the device, so it doesn't use that precious bandwidth that the host provides, and that is connected to the host. So once the data is loaded, the host, the device runs the compute all within the device. It doesn't leave the device. And once the compute is done, the data is copied back to the host. And that's pretty much what it takes to convert a regular program into a computational storage enabled program with APIs. Now let's look at the APIs themselves. So here we're using the same example, but now we're applying what are the APIs involved to convert this application. So here I'm going to use this as a very simple use case wherein you just need 5 steps to convert that example with APIs. So in the first case, you are looking at discovering the device and the functions that are available within the device. So let's take the case that the function is built into the device, and that is the decryption function. So first you use CSX, get CSX from path, that is you find your device for the data that you want to work on. And once you get that, you get the function that you want to work on, which is your decryption function. Once you have that, the next thing you would do is allocate some memory on the device. And you go about allocating memory on the device by using CSAllocMem. And the next thing you would do is you would load data from the storage device into that memory that was allocated. And for that, you have the CSQ storage request. Now, we have started with the definition of storage request as a general purpose API that can load or store data from storage into the device's memory. And we have defined today for block and file type usages. But this is, as it is an extensible interface, we plan to add others in the future, be it key value, object storage, and so forth. And you could also add your custom data type, file system type usage in the future if need be. And that's the beauty of the APIs. So once you have the encrypted data loaded, the next thing you would do is run the compute. So you queue your compute. And for that, we have the queue compute request. As you can see, we are using similar names as a queue storage, queue compute. And queuing the compute would work on the data that was loaded in the device's memory. And once that data is worked upon, and the next thing you do is you have your results, you'd like to copy those results back to the host. And for that, you use the copy device memory request, which is queue copy mem request. And with that, you kind of, with 5 steps, you have enabled your program to use the APIs to have, in this example, decryption of the data that is loaded on the SSD copied back to the host. So 5 steps. You have 5 or 6 APIs here. That's about it. That's all it takes to convert a regular program into your SNIA CS API level usage as such. So okay, so with that, let's cover what we're going to do next, and I'd like to hand it over to Jason.
Yeah, thank you, Oscar. So what is next? So first of all, if you want to know a little bit more about what we're doing within SNIA computational storage and all of our activities, we certainly encourage you to do so. The technical working group is where we're doing a lot of the development, both on the API and on the architecture. And you know, we're still active and we're still working on things on a weekly basis. And so if you aren't part of it, then certainly you're welcome to join us. On this slide, there's a lot of links that are shown here, and if you download the slides afterwards, you'll be able to click on them to for example, take you to the technical working group page within SNIA, or even to find out if your company is a SNIA member and whether or not you want to begin contributing based upon your membership status. In addition, there's the Computational Storage Special Interest Group, and this is the group that's fostering acceptance and growth of computational storage, and we'd be happy to have additional folks join us on that and help determine what is the way forward in terms of how should everyone be using computational storage and making sure that we're all finding great new use cases for it. If you're just interested in reading and providing feedback on the both the architectural document, the architecture and programming model, the version 0.8, as well as the API version 0.5, we would definitely welcome that. Obviously, we've covered at a high level some of the things that are included in those documents, and so you can click these links and go off and download yourself a copy. They're publicly available. And then there's a place on the SNIA website as well to submit feedback and give us whatever feedback you have. And there's a link down at the bottom of the slide to provide that feedback. So with that, we definitely thank you for watching our webcast, and we want you to rate it and give us any feedback that you have. A link to this webcast and the PDF of the slides will be posted to this SNIA website, so that you can go download a copy and peruse through them at your convenience. And then there's lots of other videos and webcasts that are available from SNIA's educational library in addition to the computational storage. So if you're wanting either more on computational storage or some other topics altogether, then definitely check out the educational libraries. And then the Q&A from this webcast will also be posted on a blog. And so you certainly take a look at those questions and answers and see how they relate to you. And so we don't want to wrap up, of course, without taking your questions. And so we encourage you to type your questions in and let us know what's on your mind, and we will do our best to answer them. So I'm going to turn it over
And
to Scott to help moderate those questions.
absolutely, I'm back to help with that. The first one was politely answered by Jason as part of the wrap up. The slide presentation will be available after the fact on the SNIA website and available in the Bright Talk library as well. So we've got quite a few questions that did come throughout the course of the presentation, and I thought we'd take a chance to stab at those. So one of the first ones came in is where can we see this standards-based technology, or where can we see this being implemented in the marketplace? So I'll jump in and take that one for a first pass and say that there are products from vendors in this space that are all participating in this working group. And the whole purpose of kind of the genesis of this was to get us all on that same page. So generally speaking, in most standards bodies processes and most standard release processes, it takes an iteration of a design, whether it's a generation or an update to a product, to be able to see those come to fruition. So there will be a bit of time once we get these standards published to have those products available. But in the meantime, if you are interested, you can certainly find resources around the vendors that provide products in the marketplace today. So if we keep kind of with that first part of it, Jason introduced one very high-level look at what a use case could be, and there's an additional question here about are there additional use cases and where can I see them and get more information? So why don't we throw that one over at Bill?
So yeah, so there's a couple of things there. One, if you download the architecture specification, there are a series of annexes of use cases. But in addition to that, and something that would be very interesting to you, is that we will have use cases illustrated in the SNIA booth, both at OCP Summit, taking place November 9th to 10th in San Jose, and at Supercompute 21, taking place November 14th to 18th in St. Louis. Both of those are also available virtually as well as in person. So please check those out, and you can get a lot of information of use cases. And some of these are, all of these actually are real life use cases that have already been implemented.
Awesome, thank you very much. We'll shift gears and throw it over to Oscar with the CS API library vendor specific, or is it generic, and how's it going to be provided?
Right. So as I mentioned earlier, the API library is supposed to be generic because it's an abstracted view of device-specific implementations. So that way you get one API usage across different device types and also across different vendors. So this keeps the standardization as close to as possible to just use one interface. Yeah, thank you.
Thank you, Oscar. So we have a pair of questions actually that are somewhat related to one another that have come across, with one that just came in and one earlier in the presentation. So will the API and architecture work with future interface technology, CXL and others? And the follow-on to that, if you will, is how are the collaborations taking place between CXL or other technology consortiums? So Jason, do you want to tackle that one for us?
Sure, I can take care of that. So the architecture document in no way, if you think back to some of the diagrams that we shared, we don't specify the fabric at all. It's very fabric agnostic. So any fabric could theoretically be used to implement computational storage. It seems the way that the industry is trending right now, that NVMe is going to be the first fabric to support computational storage with some of the work that they have going on over there. But that doesn't preclude other fabrics from supporting computational storage. CXL is a very logical progression for computational storage, and there are, as Scott had mentioned earlier in the recent Storage Developers Conference, there were some presentations that touched on those topics as well that you may want to check out if you haven't already. And it seems logical that that CXL and computational storage will at some point become connected. At present, there isn't an industry-wide involvement, but I think that will eventually happen. But from a SNIA perspective, there's nothing that prevents it.
Well, thank you very much, Jason. And to add into that and to close out one of the other quick questions, I'll take this one as far as the question, as you mentioned, you're working with NVMe. How are they working together? To follow on to what Jason had stated, the concepts behind what we're doing today with the SNIA architecture is to put the framework together to drive forward the technology and efforts. The fabric, as was mentioned, if you will, by both Bill and or Oscar, is that interface, that technology that's used to communicate with these devices. So that could be NVMe, CXL, or other products. So for example, there's a collaboration agreement where we share content between what NVMe is doing and what we're putting together, so we have an alignment of the two particular solution sets, and we're able to drive those things forward. So we'll throw one back over to Oscar. There's one in here that says system memory is required for PCI NVMe SSDs. How does computational storage bypass system memory? Why don't you give us the answer to that one, if you will?
Right. So traditional usage involves system memory, and what we are trying to do is using computational storage, we have device memory that is used to stage the data and work on the data, and then collect the results of the data that is worked on, and either use that using specific APIs to copy data back to host. So the work is done within the device, which means there is memory within the device that is available for the computational storage functions to work on. So it's slightly different from your host-based model where you use host memory to use that. So yes, so the device may have one or more memories that is used for the compute.
Thank you for supporting that. And again, yeah, the concepts of computational storage as a whole is to not eliminate the traditional use cases of the SSD architectures that underlie them if you're using a storage device, but to really augment those and take advantage and free up resources in other ways and technology use cases to that point. So, so we'll give one back to Bill on the CS version 1.0 and OS support. Can you give us a quick comment from that perspective to support that question?
So CS 1.0, our primary thing that we are focusing on before we get to 1.0 of the architecture is trying to understand the security implications. SNIA has a security technical working group that has some of the leading experts in security within the world that are part of that group. They are looking at our architecture, and we are coming up with a set of recommendations that recommend how you would need to secure things and what you would need to secure in order to provide a secure environment for computational storage. And I say that they're recommendations only because the architecture is a framework to design to. It is not a set of you shall do things a certain way, but rather here's an architecture that you can fit within. And then we can build the API, etc., through that. So it will be recommendations for how you do security. Once that work is complete, we will be able to release version 1.0 of the architecture document and anticipate Q1 of 2022 for that. There are efforts going on to open source development for the API that should be available also in that same time frame.
Thank you very much for that. We have one left, and I'll go ahead and tackle that one since I seem to have been the least friendly in the conversation. I've got to make up for what happened at the beginning of the conversation. There's a lot of terms that are used on this call, acronyms and such. We had all kinds of 3 letters and 4 letters going on. Jason touched on it throughout the presentation, but just to wrap it up and to kind of put in a closing comment, all of the materials that we've gone through today are represented within those publicly available documents on SNIA.org. There's a great SNIA dictionary for the primary use case definitions. So things like CSX for computational storage devices, CSD for drive, and things like CSE and CSR, those types of things. The additional definitions are also placed within the architectural document as they needed to, or the API document as appropriate, to drive the consistency of that information. We do encourage heavily that you go out and look at that content, and if you are a member thinking to be a member, join us. If not, again, that's your perfect way to see where we're going and have your comments heard, because we love to hear from those that are out there hearing this information or taking a chance to read it, what you think can be done differently. So we have one last question that's coming in, is what's being done in SNIA to implement data protection, i.e. RAID and CSDs? Can data be written striped to CSDs in such a way that it can be computed on within the drive? So I'll open that up to everyone since we're kind of on the last minute or so, if there's anyone who'd like to throw out the first comment.
So what I would say about that is, as we defined the computational storage array, the array could actually be developed in such a way that it could provide computation on data that is striped across multiple physical devices within that array. We are not defining that architecture. We're leaving that up to the vendors that provide computational storage arrays to actually define how they perform that, but we by no means preclude it.
And I would agree with that comment as well. There's lots of opportunities for continued growth on the products. There's still that crawl, walk, run kind of concepts, very much like other standard bodies have iterations of designs and architectures. We'll continue to evolve this. This isn't get it to a 1.0 and call it soup, if you will. So again, there's great opportunities for additional support of that and other architectural directions. All right, we are at the last 30 seconds of our conversation, so we do appreciate everyone's attendance. Again, thanks for watching. If you can, do us a favor and rate the session for us as well. Don't count my technology faux pas at the beginning against us, and hopefully the content was technically depth enough to get you interested to go ahead and check it out. If you are going to be making it out virtually or live to the pending events of OCP and SC21, we look forward to face-to-face or e-meeting any and all of you. So as we get back into the mainstream idea of seeing each other in person. So thanks again, everyone, and we hope you have a wonderful rest of your afternoon, day, or evening as it may be appropriate.